After the tone, please state your name followed by the pound sign. Your line has been muted.
Cleaners and solvent sites. I'm going to try to skim over a lot of stuff because most of the information is going to be in the archives for the seminar. Want to give you a quick background of company background. We've been in business for about 16 years. We're based out of Orange County, California. But over the last 6-7 years, we have been expanding to numerous states around the country, and we're now in 15 to 16 states around the country with storage locations in 9 to 10 states around the country. We have a very close working relationship with consultants and contractors in many parts of the United States. We help manage the remediation project from beginning to end with the consultants, and we feel that the synergy that we have with consultants around the country has been nothing but fantastic. We are not a consulting company. We are a vendor company. But our experience in different parts of the country has been that when consultants work closely with us, we find that closures come much faster, cheaper, and the important thing is we get closures. That's really what's important. We have systems in different parts of the country so we can move and mobilize anywhere very quickly. We have trucks like you see here, which look like a rider truck, and inside there we've got a 25 horsepower liquid ring pump extraction system, so a high vac system.
Oh, white.
It's got its own diesel tank and generator. It's got a propane tank, and essentially it's like a total system that can mobilize anywhere in the United States. Right now we have 16 of these trucks, and we have placed them in many of the states that you see there in the lower section of the slide. The equipment, you can see the truck. You can see it from the left-hand side to the right-hand side. You can see the generator with a diesel tank, which is enough to run for at least 7 days. We've got the thermal oxidizer and the liquid ring pump system with the electrical control panel. And we've got a propane tank, which will provide supplemental fuel. And we get our diesel and propane supplied at the location so that we don't have to carry it with us. You can see the dimensions there. The truck is basically like a rider truck. And when it's closed, it doesn't look like a remediation truck. So people at gas stations don't really have to worry about, this open thing with the equipment, etc. It also provides security. And also, it's a low noise system. So when you're next to apartment complexes and houses and residences, it has a very low noise. And many times, gas station owners actually come up to us days later and ask us, when are we going to start, not realizing that we had already started, days before. We also have a whole fleet of groundwater treatment systems that we can take to different parts. We realize that in many cases vac truck costs are quite high for the vac truck plus the offsite disposal, when we can get an NPDES permit or a sewer discharge permit to work with cleaning the water on site. The last on the right-hand side, we have about 20 of these chlorinated trailers. We have a patent pending process on that, where we have juiced up the liquid ring pump system, and we can extract PCE, TCE, and other chlorinateds, and work with carbon at numerous sites around the country.
Hey, Noel.
Yes?
Just wanted to jump in. Do you mind speaking up or getting closer to your phone if possible? I have you turned all the way up, and it's a little tough to hear.
Okay, sounds good. Can you hear me better?
Great, that's perfect. That's perfect. Thank you.
Thank you. So we can handle various constituents like gasoline, heavier hydrocarbons like diesel and jet fuel, also chlorinated solvents, PCE, TCE. Of course, we have different trailers for that. And recently, we've been able to even pull up oil like Bunker C, and we've even worked at the reserve pit here in the Los Angeles area pulling up oil at an oil reserve pit. So that has worked out very well with our systems. From a technology standpoint, again, high vacuum dual phase extraction, a lot of people know about it around the country, but we have a patent pending process within our system on how we have juiced up our system, and our systems are very, very powerful, and we have them on all of our trucks and trailers that we use around the country. The extraction process, again, you can see one of the trucks. You can work with high vacuum vapor extraction, where you have just vadose zone. So a lot of people think of us as just for dual phase extraction, but we can also do a high vacuum vapor extraction in the vadose zone, and we've been very successful with that. This slide basically depicts that the longer we are at the job site, the lower we can depress the cone of depression, and the easier it is to clean up the site. And that's something that I don't believe these 8-hour and 1-day and 2-day events really do. But when we are at a site for 30 days and 60 days and 90 days, we can lower the water table sufficiently to really do a cleanup at a site. From a system comparison, this is a very important slide. As you can see, if a fixed base system was to be installed at a site, easily in California, sometimes it doesn't even take 15 months. It could take 18 months or even 24 months by the time you get all the permits and the city permits and working with the contractors to install a system. Well, the plume size is getting larger. Now, if CalClean was deployed to a site, we could do a series of 2 or 3 or 4 30-day events. We could probably get to closure levels in 6 to 7 months. And we've done this numerous times. So this slide is really a telltale slide. We have a bunch of comparisons between our system and standard SVE and pump and treat. I'm going to just go through what we do. I think everybody knows that the HVDP systems are very powerful, but we have truck-mounted systems that can go anywhere in the country. The high-capacity systems, they can extract 5 to 50 gallons per minute of water from the ground. You can destroy up to 130 pounds of hydrocarbons per hour, which is quite a lot. Again, it's a high-vac system, so we can pull up to 29 inches of mercury, which means that the radius of influence is quite large. We can pull vapor and groundwater and can also lower the groundwater table to address what's in the cap fringe and the saturated zone. We can mobilize to a site very quickly because we have systems placed in 9 different states around the country. When we come to a site, all we have to do is we open up the side doors like the cafeteria-style doors. Within 30 minutes, we are up and running, extracting from a site. I'm not sure if there's any other company in the country that can work so quickly. We can adjust the number of days of operation. So if we're planning to do a 30-day event and concentrations drop off, well, we can pull off the site and go somewhere else, kind of like time sharing. The amount of time that we are at a site, we're only occupying space when we're at the site. When we're finished, we're gone, and that site can be used for other things at these small gas station sites. I think one of the important things I brought up earlier was the low noise operation. It's great for residential areas, and as you know, a lot of gas station sites around the country are next to houses and apartment complexes, and the last thing we want to do is have complaints from neighbors like a lot of these standard systems have at sites. We also do something that I don't believe any other company does in the country, and that is we man our systems 24 hours a day. So with a person there, we can adjust the stinger depths on a daily basis, and that way we can maximize recovery and get the job done faster. No capital cost outlay. So when we do a project where there is no cost to build a system and then have to deal with salvage later on and installation and all that type of stuff. Closures can be attained earlier. In California, the average length of time it takes for us to get closure at a site is basically 3 to 4 30-day events. Now, I realize that in between there might be some time, and then after the events, there's going to be verification monitoring. So that could take, an additional 1 year. But the amount of time it takes for us to work at a site, a typical gas station site in California, has been 3 to 4 30-day events. Again, no shutdown of the station. Of course, station operators love that. And there's no long-time commitment or cost of decommissioning here. There's no weekly O&M costs, and we can get closures faster, which means the liability can be released quicker. The system advantages are we have the lowest, the most cost-effective system with the lowest dollars per pound of hydrocarbon removed. Recently, at a presentation in a state, one of the people who was joined us in the presentation today, they asked me about what the number was, and it's around $5 per pound. That has been the average over the last 16 years for CalClean. I know that a lot of other states are quite surprised with that because many of them have been in exceedance of $100 a pound to do work. Again, no capital maintenance cost outlays. We can move very quickly to a site. We don't have to shut down the operations. We can work in neighborhoods, and we occupy less space at the station. But the capacity of the equipment is very large. At one of the job sites we did in California, we actually pulled water from 270 feet. We realized that water in a solid column can be only pulled up 33 feet. But with holes and stingers placed at certain depths and the way we managed it, we were actually pulling up water with a stinger, not a pump, from 270 feet below ground. Here in California, we have obtained various locations permits, and California is a place of permits and permits and permits. So you can just imagine how much easier it is to work in other states around the country where we don't have to obtain as many permits. We also guarantee 100% uptime. So, for example, when we charge for a 30-day event, if the unit's down for a day, we add a day. If it's down for 2 days between that 30 days, we add 2 days. So we guarantee 100% uptime. We have our employees have been with the company for quite a few years, and we've had the company for 16 years, and the average length of employment in CalClean is around 12 to 13 years, which means our employees have been here for a very long time, and they've got a lot of good technical expertise and supervision. We have 16 trucks, and basically we have over 200 remediation systems. So we have a lot of firepower that can be mobilized to places around the country. Some of the things that we've done over the years to enhance our HVDPE, the simplest has been the use of air sparging. Obviously, we won't do that when free product is present, but once free product is removed, we have worked with consultants to install very specialized air sparge wells below the source area, and with the air sparging, it has increased our ability to clean up a site faster. We've also been able to use remove diesel-free product, and the way we do that was we obtain that by flushing the ground. Obviously, diesel will not volatilize, but it will come up with the water. In some cases, we use surfactants to assist with diesel cleanups, though we've been able to pull up much more diesel with our HVDP rather than the surfactants. We've been able to clean up groundwater sites quickly with the high vacuum systems, and we help consultants in designing appropriate extraction wells and injection wells, because as we all know, I can't do my work properly without a proper infrastructure. So obviously it starts with a good site assessment and a good site conceptual model, But then after that, once we've got delineation, we work closely with the consultants around the country so that a proper extraction well with a proper screen interval, with the proper lithology is installed, and then, hey, we get good results with good equipment. And then we use periodic extractions where we go to a site for 30 days, we leave, go somewhere else, and we come back again. And this has helped to address the interim rebound. Here's an example of HVDPE with air sparging. At a location, and these are locations in California. We started these sites where there were 6,000 and 10,000 and 20,000 ppmv, or even with free product. But once the numbers went way down at the tail end of the, say, 30 days or 60 days or 90 days, when we added air sparging, the numbers jumped up. You can just see we were getting 10,000 ppmv where previously we were getting 600 ppmv. So we know one thing, HVDPE can really enhance our operation. So we're not just a one-horse carriage here. We're using another technology, which is air sparging, along with HVDPE to enhance and speed up the cleanup. This is something that we're starting to move into where performance-based contracts is something we're very interested in around the country. They reduce overall project costs. We can do quicker cleanups because we can use multiple systems at the same time. And I'm going to talk about a site in Missouri that we started in June last year, and we're very close to being done at this point in just over 1 year. We feel that it's better for the environment because you can get guaranteed results, use cutting-edge technology. More and more states around the country are moving towards these performance-based contracts. Yes, they might be a little bit more expensive, but in the end, if we can take on the risk and get the job done, well, in that case, we probably are the cheapest then. Florida has seen a 64% savings, and I'm sure that other states have seen lower administrative costs because in a performance-based contract, you don't have so many pieces of paper being shuffled around between the consultants and the regulators and the insurance funds, et cetera, et cetera. And of course, the risk is transferred to the contractor. So this is something we are interested in all around the country. At the site in Kennett Conoco, it's in the boot heel of Missouri. We took on a performance-based contract here, and I do want to thank the Missouri DNR and the Missouri PISTIF for being a part of this because this was a very difficult road to get this contract signed last year. But once it got done, we started at the site. MTBE has affected the city drinking water wells at the site. There was free product up to 3 feet in 18 wells on-site and off-site on 4 properties. The lithology was kind of relatively easy to work with, and I give you that, but it was a very large project. So in this project, we actually used 4 systems. 2 systems on-site, and then 1 system to the property to the east, and 1 system to the property to the south. Within 4 months, we had already pulled out all of the free product, and the consultant who was on the site before was hired by CalClean to continue to be the consultant for this project. And they continue to date as a consultant for the project. Once the free product was removed, we installed, we meaning the consultant in Missouri, installed 5 air sparge wells, and obviously the amount of mass removal was quite high. From June last year to June this year, we've already pulled out almost 3 million gallons of groundwater. We've reduced the on-site groundwater concentrations are below the risk-based levels for the site in all of the wells on site. And now we're working on the off-site wells to try to get those to meet the levels approved in the cap. As of June 30th, we have pulled out 63,000 gallons of gasoline. I think all of you will realize that is just an astronomical number for a gas station, when most gas stations are around 1,000 gallons of gasoline in the country. So 63,000 gallons, you can see with a performance-based contract what we can do with one person operating the site and 4 systems operating on different sites. Here is the map, which shows all of the wells in red had free product. By 4 months after we started in June last year, we had already removed all of the free product on these different sites. And right now, the on-site where it says former Kennett Conoco Station meets the risk-based levels for closure. And we're now working at some of the off-site locations to get them to closure levels. So our recommendations are to conduct 30-day long-term events instead of 8-hour or 3-day or 5-day events, because the cost of mobilization and getting to a site for a short-term event is quite large. So those costs are built into those events. So when you do 30-day events or 60-day events or 90-day events, you have economy to scale, and so costs per day then get much lower. And something I did not mention earlier, we have a website which is CalClean.com, and in there we have our rate schedule for work all across the country. Another thing is treatment of groundwater. We all know how expensive it is to deal with groundwater that's affected. But getting a sewer permit or even an NPDES permit and treating the water on site is the best way to handle it. Using vac trucks and all that stuff, okay, for a pilot test, I can understand that. But for these long-term projects, we prefer to get a sewer permit or an NPDES permit or both and work with treating and discharging the water on site. At all of our projects around the country, again, I mentioned earlier, CalClean is not a consultant. We work with consultants around the country in doing aggressive cleanups so that we can keep the costs down. The remedial well design location is very critical to our cleanups, and I mentioned earlier, we work with consultants to come up with the right screen intervals for the ground. Also, consultants. There are different types of consultants around, and we work with consultants. So we've got projects in Missouri right now where some of the consultants are not very good in remediation, but we're working with them to train them so that they can do a better job with cleanups in Missouri or some of the other states. I'm only bringing up Missouri because we're working with several projects in Missouri, and we really love working in Missouri. The folks with the DNR and PISTF have been very nice to work with, and I thank them for all their help. Again, conducting 30-day events to take sites to closure is something we strongly recommend. I think this is our most important slide in all of our slides because it says the word case closure and counting. In 16 years since we started in 1999, we've had over 500 case closures that we've affected. And you have to also realize that a lot of these cases that we get are difficult cases because these are sites where other people could not get closure because of weak equipment or inappropriate screen intervals or other things. And we went in and worked with either the same consultant or another consultant, and we came up with working on, I think all of you know the 80-20 rule, right, where the last 20% takes 80% of the time and the money to do. Well, that's where a lot of our case closures are. And I guess you have to go and get stuff. Here in California, people have told consultants and owners to contact us. And all of our closures have basically come in California and Florida, but now some of the closures are going to start coming in Arizona, Idaho, Utah, Missouri, Florida, and some other states too. So we've come up to a point where we want to see people have comments. One question that somebody had was, what are the depth limitations of the high vacuum system? I think I mentioned this before. At Mammoth Mountain in California, we actually had our system where we were pulling water from 240 feet, and we pulled the water all the way to the bottom of the well, which was 270 feet. So I hope we answered that question. So, Drew, at this point, if there's any questions, we can open that up.
All right, great. Anybody want to go ahead and use the chat function and send a question my way if you have any? Give it just a minute or two to see if anyone wants something answered. All right. Well, nothing so far, Noel, but I'll keep an eye on it. And those of you, maybe if something comes up later, at any time, feel free to use that chat function, and I'll make sure I get your question in for you.
Sounds good, Drew. Thank you so much.
Thank you, Noel. All right. Well, I'm going to go ahead and unmute our next speakers. And without further ado, I will introduce Tom Fox and Edward Winter. And Tom, I'm going to go ahead and make you the presenter now.
All right, actually, I'm going to be passing this over to Ed because he's going to start. Okay, great. And just a heads up to all of our listeners, Tom and Ed will be speaking for about 50 minutes today. That's 50.
Oh, no, Tom. I'm going to pass it back over to you. Okay. No, okay. So we'd like to talk to you about lessons that both Kentucky and Colorado have learned in the use of activated carbon injectates. Now, Tom and I have had the opportunity to do this, or at least parts of this presentation before, and we'd also like to thank Drew and NUIPIC for having us. Now, before we get started, let me ask first, is the volume okay? Can everybody hear us well?
Yeah, it sounds great.
Good, good. So as a point of politeness, let's start with acknowledgements. The first, I need to move this forward myself, do I not? Let me figure out how to move the slide again. Aha, there we go, moving the slide. So we'd like to acknowledge Demin Fan, who is a postdoc with US EPA and has spent some time trying to collect the information regarding carbon injections and consolidate it. I believe he's working on a publication. We'd also like to thank Scott Noland of the RPI group. They produce and market the BOSS product. We have 2 injection contractors, actually 3, but 2 so far that we've worked with regularly, is AST Environmental and also Chase Environmental, that they don't happen to be on the slide. We'd also like to thank Jess Taylor of Remington Technologies that has the Kogak product. Each of these have provided information and pictures and things that you will see in our presentation today. Now here's what we want to cover. We want to talk about high-resolution site characterization, actually identifying the mass. We'll talk about the properties of activated carbon and how activated carbon amendments work, the method of their application, some sense of how much needs to be injected, the injection and process issues, our recommendations from some of our experiences, and then, of course, we'll move on and see what questions you have for us. As far as Kentucky's record goes, and this is a little bit dated, but it still gives you a sense, we use high-pressure injection to cope with the low permeability geology in the state. These are fine-grained clay soils for the most part. We've placed an extreme emphasis, I think, on building a good, high-quality conceptual site model before we move into employ remedy. And we will be, both Tom and I today will be emphasizing that. And out of 72 sites that we have treated with carbon, 41 have achieved NFA. Approximately 10% needed a second injection, or should I say the project manager chose a second injection. It kind of depends on how big a hurry you're in sometimes. There are 7 present where the contractor has requested NFA, and we may or may not have acted on it at this time, and 24 that are in monitoring stage. 19 of the 24 are less than a year old. Now I'll pass it over to Tom. There you go, Tom.
All right. Thanks, Ed. In Colorado, we've been using mainly BOSS 200 for the past 10 years or so. We had treated over 200 facilities since 2005. It was only recently that we began to go back and relook at some of the information, which we'll get into later. We usually tried carbon injection when other methods had been unsuccessful or proved impractical. Often we saw significant reductions in dissolved BTEX, but we also noted that there was visible carbon usually in the monitoring wells, which could be taken as good information or bad. We also noted that there was often some rebound or even a second or third injection treatment necessary. About 15% of our sites closed with NFA, and I caution everybody to take this NFA standard carefully because every state has a different NFA standard, no further action. We have found our best treatment occurs where we're treating in small focused areas, something about the size of a tank basin, and where low concentrations of benzene are found. Some of the things we would like to bring to light are sampling uncertainties with a lot of the information that we all gather, and that is we have all kinds of field biases that creep in when we collect samples, both to characterize a site and also to monitor it for closure. And I've listed a lot of these here. We have field problems with sample collection and location, sample preservation, whether it's iced or acidified, and the number of samples, in fact, that you may take either over time from one well or by the volume of soil samples that you collect from the site. Geologically, we have a lot of internal biases due to soil type. And from analytical biases, if you collect it by the method of collecting soil in a sample jar and then sending that to the laboratory has some discretion as to what sample they actually take out of the jar to run through the GC. In addition, we also have some sometimes dubious field measurements that are collected by consultants. The whole point being here is a lot of the precision is lacking in trying to characterize sites. Which brings us to trying to solve that dilemma, and that is trying to look at some high-resolution site characterization. And here what we're trying to do is to get a better estimate of the hydrocarbon mass and where it is in order to refine our conceptual site model. A lot of the methods that are in use around the country deal with MIP, LIF, and HPT probing. There is also some continuous soil sampling and laboratory samples that are being done, mainly by RPI for free. And you can also use geophysical methods either from the surface or downhole to get a better idea of what type of materials you're dealing with. It's important to remember, though, that when you use all these methods that you have a good idea of how the tool works and what you expect from it and what its limitations are. And then also you have to sometimes get assistance from the vendors in order to interpret the results. So be careful that you ask what you're going to get from your contractor. This is just an example of MIP output for those of you who aren't familiar with it. And basically, I know this is a bit small, but the lines that are shown there indicate zones that are showing some impacts from PID and FID responses as the probe is advanced. And these tools are really critical to help you dial in and target what zones you need to treat with carbon injections. It is much preferable to spend the money to characterize a site in detail up front than to simply shotgun the site with carbon and spend a lot of money in wasted remedial effort. Some of the high-resolution geophysical tools that are used are, as I mentioned, downhole logging and some superficial 2D type methods which basically take a vertical slice through the surface that you then try to piece together like a cross-section. Now, Kentucky has basically been doing this more so than Colorado. And Ed, back to you.
Okay. So the properties of activated carbon. I want to talk about the sources of activated carbon, something about its surface area and particle size, pore size, structure, and adsorption. Oh, let's get started. See if I can move it. There we go. Activated carbon can be produced from almost any carbon source. It really depends on your starting material and the final product you want. So depending on the source, you'll have a varied porosity and structure. The structure and porosity arises from the difference in the size of the graphic plates. So if you've ever seen a picture of graphite, it looks like a bunch of pieces of paper stacked up on top of each other. And so depending on what you actually roast your activated carbon from, you'll change how closely those plates are associated and how big those plates are, in other words, the overall area. For lack of, I guess, just to give you a fun term, it's called aliphatic dislocation, which is a measurement of how those plates relate to one another. So for carbon injection, what has been used primarily is activated carbon from bituminous coal. And this is really due to the hardness of the carbon, its abrasion resistance. It also has a low ash content. Cost, coal is relatively inexpensive. And finally, the size of the carbon plates and closeness, or that aliphatic dislocation I was talking about, is good, or at least it's probably best in bituminous coal. The activation process itself is essentially combustion in a low oxygen environment. That can be done with steam. It can also be done with chemicals. That's not real important, but at least as far as what you're going to use. There is a note on the slide. It's the second note, and it says it's preferable to use virgin, not regenerated carbon. And I will come back to that in a minute and explain why that is so. So the drawing you're seeing on the right-hand side of this slide is only intended to illustrate the relationship between pore types. This is not what activated carbon looks like. But two pore types, the macropores and the mesopores, are primarily, you can kind of think of them as highways. They allow the contamination to enter into the carbon, and it is the micropores, those that are 0.002 microns and smaller, that actually bind up the contamination. So those could be thought of as the parking lots where you hold the contamination. Now, there are two kinds, there are actually multiple kinds, but just for simple categorization, there are two kinds of activated carbon, granular and powdered. And you can see it right there in the hand. Let's see here. The micropore surface area on a weight basis is really the same for either granular or powdered. So you're not really losing absorption capacity. What you're really losing or gaining one versus the other is packing. So you can see that the granular carbon would be used in flow-through processes in water treatment plants, or if you wanted to build barrier walls and you didn't want to kind of back up flow because you have more spaces between the carbon, where the powdered carbon is typically used in mixing with liquids and trying to pull contaminants out that way. So you would see a powdered carbon example, say in a packing bed, something like that. Therefore, it really kind of depends on what your goals are to which carbon you'll use. The absorptive capacity doesn't really change. And in fact, you can just keep grinding carbon down to finer and finer grinds, and you really still retain the same absorptive capacity. Now this is a better, more realistic picture of what activated carbon looks like, and it should be realistic. It's a micrograph. And I think it kind of looks like hamburger meat. It's one way of looking at it. Another way, it looks very similar to graphite. And I really kind of want you to look at this picture and imagine those spaces and what happens in the where the contamination sorbs in those spaces. There are two kinds of adsorption processes which are occurring to pull molecules from the bulk fluid. And that's a kind of an important side point, that if you're injecting carbon in dry soil, it's not going to work. It really is carbon and water. They kind of go together, so you're looking primarily at injections below the water table or in the capillary fringe. So of the two types of absorption, one of them is a physiosorption, where you have these electrostatic attractions, sometimes they're referred to as van der Waals forces, between the sorbed molecule and the surface of the carbon. These interactions are relatively weak and they're reversible. So you can adsorb, I should say benzene onto the carbon, and then that benzene could be reversibly released, and we'll talk about that later. The contaminant carbon surface interactions occur through these van der Waals forces, sometimes also called dipole forces, and the activated carbon plates induce kind of a, I don't know exactly how to say it. I'd say it's kind of a neutral organic situation with the intermolecular bond. So anyway, put it this way. A sorbent is very comfortable with staying in the carbon. Now, there is some chemosorption where you actually have bonds to the carbon that are permanent. And this goes back to what we said earlier, why you don't want to use reactivated carbon. You can take carbon that's, say, been used in water treatment, you can reheat it, and then you can try to use it again. The problem is there is a certain amount of chemosorption, especially if it's been exposed to heavy metals, and you're not going to drive those off. And that might be as much as 20% of the absorptive capacity. So, and you also don't want to add heavy metals to your site, even though they'd probably just stay on the carbon. One other note on this slide, or two other notes I should say, kind of a fun fact that says 5 grams of carbon has the surface area equivalent to a professional football field. So there's a lot of absorptive capacity between each of those plates that you're seeing in the diagram or in the picture. And then there's the iodine value. This is of less real meaning to you. It's just the way the industry uses to kind of judge the quality or adsorptive capacity of the carbon. It's going to be very important to you if you release large amounts of iodide onto the site, but since most of us are interested in petroleum products, the iodine number doesn't really correspond directly to the iodine number. Slide 16 is intended to provide some sort of appreciation for relative size. In short, BTEX is small enough to enter all the pores, or activated carbon as well as all the pores of activated carbon as well as all the pores of clay and silt. Microbes, however, can only enter the macropores, the largest pores associated with activated carbon. Microbes can enter sand, silts. So in order to allow microbial activity, you're going to need to open up clay formations and try to get as much movement of water through those formations as possible. Now it's time for Tom. Here you go.
Thanks, Ed. All right, the next section we're going to be talking about is an overview of how activated carbon-based amendments work. And basically, there are two processes at work, and then we hope to add a third process by adding some amendments to the activated carbon. So carbon, as we've been talking about and Ed has talked about, obviously has some very large absorption capacity. What we also know is that petroleum degrades over time. So is there some way that we can accentuate those degradation processes to then free up absorption sites on the carbon to absorb yet other contaminants and continue to pull contamination out of the groundwater? So basically, this is the circular process of adsorption, degradation of the contamination, regeneration of the carbon, and then continuing adsorption of the carbon that we are seeking to involve. Now, some of the advantages that are claimed by a lot of the carbon vendors are that you have a very fast response. This can occur almost immediately and sometimes weeks to months later. This is strictly due to the absorption capacity and characteristics of carbon. This is really obvious when you do the injection, and fairly quickly you'll notice wells nearby will rapidly have a decrease in contamination concentrations. The second advantage that the vendors tend to provide is that there's no rebound or very little rebound. This results from sustained treatment. In other words, this regeneration process I just mentioned counters back diffusion from the soil. As it comes off the soil, those molecules are absorbed onto the carbon, and that a limited number of injections would be needed. Coming back to Ed's earlier diagram, we've added here where some biofilm in blue has accumulated on the surface and the larger macropore openings of a carbon molecule particle. And here we see that adsorption is very dominant at the beginning as everything gloms on, and then biodegradation becomes a little bit more dominant, at least we hope so, and that some of the absorption capacity is not used but serves as an emergency capacity when you have a sudden slug of contamination move through, or there's a decrease in biodegradation rate for some environmental factor like a seasonal change in temperature. Basically, there are two biological approaches that go on at the same time within a plume. On the edges, you'll have aerobic degradation for the most part. The processes are the same. The degraders may vary a little bit. And then you have facultative and almost anaerobic biological degradation occurring at higher concentrations in the main source area of the plume. And this slide is simply to highlight that both of these processes do occur on every site. What are some of the indications we have of biological activity? Well, we'll often see that nitrates will drop out of the groundwater fairly quickly, almost immediately, certainly within a month. And some of these products do add nitrate, and I want to caution everybody to not be too concerned about that. From my personal experience, I've seen nitrate levels rapidly decrease to ND or background levels very, very quickly. Sulfates will also drop over time, but because sulfate is used a little bit more or biodegraded more slowly, that also tends to linger a bit more, and that's why gypsum is used as an amendment in BOS 200, for example. Dissolved oxygen will generally decrease over time as it's used because oxygen will go first, and ORP will generally be negative within the plume. These are some typical responses, this slide and the next one, of what we've seen in wells after injection. This is the instant response in this monitor well number 4 that I mentioned. It goes down, it stays down, you have good absorption, enough carbon, etc. in the subsurface. Sometimes there's a bit of a slower response, and this graph for my MW9 shows several quarters, looks like 4 to 6 quarters at least, where it took for everything to be absorbed. Sometimes we end up with a rebound issue. Rebound will often occur by the 3rd or 4th quarter after injection, and this is simply indicating you've got situations that we'll talk about a little bit later as to why rebound occurs. And rebound can also continue to occur even after a second injection, and this is usually indicative of poor distribution. I'm going to talk a little bit about the methods of application, and I'm going to talk strictly here about injection for now. Basically, as Ed mentioned earlier, you want to target the smear zone, areas slightly above and below the water table. So it's important to know the historical groundwater variation at your site, and perhaps in use with other high-resolution site characterization methods, you can target your zone a little bit better. But at a minimum, you want to look at your groundwater fluctuation zones. The methods of application, generally there are 4. Gravity feed is generally not recommended. It limits the amount of material you can get into the ground. It's very slow in general, and when you're using this, as most people typically are, in fairly tight formations, it's usually not very successful and covers only small areas. This might be recommended for materials such as plume stop from regenesis, which is a colloidal carbon and can flow through more porous materials, but we won't get into that right now. You can also do pressure injections below the hydrofracking pressure of the material. Again, you need to be able to push material in at a small pressure, and you have to have enough porosity for the material to move through. The method in the red box is the most common one used, and that's where we're doing pressure injections above fracture pressure. We're actually creating fractures, making new openings, and forcing the carbon into the material. This generally will follow areas or paths of least resistance. And what you'll see during injection is a continuous buildup of pressure to some point where the formation breaks, as it's termed, and there's a short burst of flow until things equilibrate, and you may then get flow or a series of breaking points. We won't talk here about excavations and trenches, but if you really want to get material distributed, putting granular carbon into excavations or trenches during tank removals or as across plumes, as was shown in an earlier picture, is really the best way to guarantee distribution. This gets a little bit more into methods of injection. These are both high-pressure type processes. In soft materials, you're going to be looking at a high-pressure jetting, which basically is a homogenization process typically used in sands. In Colorado, we have some areas that have basically flowing sands where this jetting method works really well to homogenize. However, I would caution that you will not go very far from the injection point with your homogenization process. Second process is hydraulic fracturing, and this is more competent materials, not necessarily hard rocks, but I'm talking about some fairly competent clays or siltstones. This is going to often require that a borehole is drilled and then backfilled with bentonite, and then later on the actual injection point is installed through that and then fractured into the formation. Sometimes sand or guar gum is used with the amendment to keep the fracture open and prop it, but I found that generally that is not used in the UST industry. Direct push injection, or geoprobing, as many of you might know it as, is really the most widely technique used for injection. There are various designs out there in the market for injection tips, and this is the injection point that's driven into the ground. The design and the injection varies quite a bit by the contractor that's doing the injection, and there's quite a bit of an art that goes into choosing the injection tip for the material you're going to be injecting into. Injections need to be done on a fairly tight spacing. In Colorado, we were doing injections on 10-foot centers as the vendors had recommended initially. Kentucky has done injections on 5 to 7-foot hexagonal grids and had much better success than we have, and we've in fact now moved to a closer injection spacing. You also vertically only want to inject over short intervals. Some vendors initially were trying to inject over 5 and even 10-foot intervals. My response to that is that it's very difficult then to control where the material is going, and to know, in fact, that you're treating the zone that you're trying to do. So try to limit yourself to a fairly short vertical interval. The initial pressures are going to be greater than 100 psi, sometimes quite a bit more, and then you hit that break pressure and the pressure will drop and you'll begin to get flow into the formation. Flow rates can vary quite a bit, anywhere from less than a gallon a minute up to 75 gallons per minute in some very porous materials. This is just a picture as an example in a parking lot of kind of a hexagonal grid that was laid out to give you a sense for some of this spacing. And on the left side is kind of a side view to show how adjacent boreholes or injection points have their injection intervals offset slightly to try to create kind of an interlaced pancake effect. And Ed is now going to pick up and talk a little bit more about carbon and how it acts in the subsurface.
Waiting for the green. Okay, you can hear me. So slide 29, the purpose of this slide is to emphasize the importance of carbon as a particle. You know, when you do an injection, you're putting a lot of material in the ground, and that material has a size. So if you recall, powdered activated carbon is in the tens of microns, but less than 40 microns. Clay and silt have pore throat size 10-fold to 10,000-fold smaller than even the carbon. So you're not really pushing the carbon into the pore throat of the clays. I mean, you might as well be shoving a bowling ball down a soda straw. It's not going to work. You are, however, opening up new low resistance flow paths in the immediate area of the injection, whereby opening those pathways for contamination movement, for the movement of water. So you change in the most immediate area of the injection, you change flow. Now, again, this is very small. It's not like you're changing the global flow across a site for hundreds or thousands of feet, but in that immediate area you are. So the two pictures I have is one to show the one on the left. It almost looks like brakes on a car. It's just to emphasize you are putting mass in the ground and things are going to move. The diagram on the right side emphasizes how if you have an area of lower resistance to flow, such as the green disk, it can drain a much larger area than you may anticipate. Now a bit about fracture emplacement. And these are some idealized diagrams originally put out by Murdoch and Slack. They're the classic journal articles in this area. And in this particular case, this is true hydraulic fracking with a propagant, gar gum. And as it's been looked at, what you find is that the fracture wants to move up towards the surface. So one issue you have to deal with is daylighting. And the other one is very similar to that, and that's your injectate coming right back up the stem of your push rig. So if you look at how that injectate curves up, and you can see that in the top diagram on the right, you kind of have a dip and a depth, and it kind of curves up. I think the way to look at it is it looks something like a Pringles potato chip is the idealized picture. Now, if you have saturated soils, that's going to increase your resistivity, and it's going to have even more of a tendency to want to turn up or come back up the stem. There are 2 points I want you to see here. Oops. Let me go back. I seem to have skipped a slide. No, I did not. Okay. So on this slide, if we can make this YouTube animation work, and Drew, you might have to remind me how to do this. I did download it, but where do I go now?
You know, it's one of the top tabs. I don't specifically remember. It's one of the options where you're sharing your screen or. Yeah, I don't remember. We might not be able to make it work today.
Well, that's unfortunate. That's unfortunate. Okay, well, so be it. What you would have seen, and that's such a letdown. But you would see as the fracture propagates, it comes out as a disc shape that tends to roll and climb towards the surface. And if you put together multiple sheets like that, you start getting an idea of what the main vision of a fracture emplacement starts to look like. So I will just move to the other slide. And this is an idealized fracture. It's actually, it's only idealized in the sense that it was drawn. This is a drawing of what they think of a real site that was injected. And you see each of these disc shapes as they interact with one another. And this would be like the main thrust of the injection.
Hey, Ed, I just wanted to jump in.
Yes.
It might be the option just to try it once. We don't have to troubleshoot this in front of everyone, but the Share tab at the top of your screen, since you're still in control, if you go to Share, one of the options under there is Share My Screen. I think that's what we did.
I believe it is. Let's see. Say Monitor 1, and then I flip over here. Can you see that?
Yes, we got it.
Ah, very good. Thank you, sir. I appreciate it. Because this
Absolutely.
is kind of worth watching. Well, now I got to unshare. Well, I think we're going a little far here. Let's see if I can figure out how to unshare the screen. Aha, here we go. Stop sharing. Okay, so now we're back to this. And the goal of showing you that was to show you some fundamental characteristics. The tendency for the injectate to want to move up, the tendency of the injectate to want to move as flat against the media in which you're injecting it into as possible, and that would be true of your formation also. And it kind of leads you to understand why it's a little bit of a random process other than having those core characteristics. And it leads you to understand that you really need to inject very close together if you're going to build a kind of, let's see here if I can make my screen go backwards, make it go forward. if you're going to kind of build a kind of overlapping of those structures. But along with the core induced fraction in the formation, which might have, in a broad sense, that kind of Pringles shape, you also have low resistivity aspects in your formation. So you can see that on the right-hand side where they're calling those natural fractures in the formation. You have the induced fracture going on, and then low resistivity areas, you get fingerlings. And you see on slide 33, if you look on the left side, you'll see that's a picture of a core taken here in Kentucky, and you'll notice that the carbon is modeled throughout that core, and that's the result of something like what you're seeing on the permanganate on the right side. Now, seemingly small openings can actually fill larger voids, and you see that here in this core boring. Now, these are various patterns seen. I believe only one of these patterns is a Kentucky pattern, the one down at the bottom of the page in green with a green box around it. And you can see that that's below the water line. It's kind of sloppy, and we get a bit of homogenization in it. The other three are, I believe, contributed by Tom, and you see the various soil types. You might see spots or small fractures, homogenization, thin veins. But for the most part in clays, we have seen that rather modeled distribution. So in summary, fracture emplacement increases local water and contaminant mobility on a small scale. The tendency for the fracture is to move upward in the formation, forming sheets that look a little bit like Pringles in an idealized sense. Simultaneously, it's looking for low resistance areas that it can kind of branch off into and staying as tight and thin as possible. Multiple injections are required to get a good overlapping pattern and deal with some of the random aspects of it. And ideally, at least their best sites, we've seen this kind of modeled pattern within the soil bores that we've taken out of the sites. The next topic has to do with how much to inject. And I'll tell you just straight up, there's a bit of witchcraft here, depending on who you're talking to. And that you're trying to accomplish two things simultaneously. Number one, you have an area, a three-dimensional area which you have to treat because you have contamination throughout that area. And that area has a volume, and that volume is going to demand a certain amount of carbon regardless of the mass of contamination that's in that volume. On the other hand, you have a mass of contamination that needs a certain volume of carbon. And you kind of have to balance those two against each other. And most of the time what you'll see is people talking about absorption isotherms and, you know, as if you can use that one thing to figure out what you need. You cannot. Your total mass is going to be those two characteristics, but your accuracy is going to depend on your conceptual site model, the concentration data you've actually collected and how well that data represents to the site and the area in which you want to inject. There's also going to be a correction factor. For some programs collect total hydrocarbons or TPH. Some programs collect BTAX, which is our program. Some programs are more prone to look at the concentrations in monitoring wells. Other programs take a good number of soil bores. So no matter what you're using, you've got to correct back to the total mass of hydrocarbon you think you have in the ground. And then in the end, you have to just ask yourself, hey, how wrong could I be? What kind of error do I think I have? What kind of safety factor do I need? I will say that it is the total hydrocarbon that you're trying to treat, and most of that hydrocarbon is in the soil, even though I would say most regulatory programs are driven by groundwater. Now there is in the soil screening handbook, US EPA soil screening handbook, there's a little formula you can use to calculate what you think your soil concentration is based on your water concentration. And it's probably good to do that measurement and look at it. For what it's worth, it's formula number 11 in the May 1996 edition. And if those two numbers are too far apart, you might wonder if you've really characterized your site well or not. Now, earlier I mentioned absorption isotherms. Carbon in general, and I'm making a generalization, depends on where the carbon came from, will absorb so much of a contaminant, of a pure contaminant, per so much carbon. So typically what you'll see a lot of the vendors say is you'll absorb 1 milligram of benzene for 1 gram of carbon. Or if you look at the chart where I have the molecular structures, you'll see a number above them. So look at the number 26 above toluene, and that would be saying that you could absorb 26 milligrams of toluene for 1 gram of carbon. So some vendors will use that kind of calculation. Typically they'll use benzene because it's the more conservative number and say, well, that's how much carbon you need. But it's really a combination of things. Now there is a slight rabbit trail here that is of some value to you. And you notice that if you're only absorbing 1 milligram of benzene per gram of carbon versus, say, your xylenes, which may be 230 milligrams of xylene per gram of carbon, that's telling you something about the character of carbon, that it likes xylenes and larger aphilic molecules much better than benzene. So generally, benzene is the last thing to absorb the carbon. And in fact, if you had a large release of a hydrocarbon that it liked better than benzene, it could release some benzene. That's not a big fear or anything, but it is just something to understand about how carbon functions. Okay, now it's time for Tom again. There you go.
Here I am. All right, this is Tom Fox again. We're a little bit past the halfway point for those of you who are wondering when it'll ever end. I'm going to be talking about injection issues, and basically this is going to focus on distribution of the carbon during the injection process, and then bringing back into focus some of the absorption issues that Ed has been talking about. So some of the things we're going to be talking about is how to get the carbon distributed, how to be aware of daylighting at the surface, also finding preferential pathways such as utilities or backfills from old tank removal excavations, for example, weak areas that the carbon will tend to move into once it finds it. Also entering monitoring wells. We'll touch a little bit on how to rehabilitate wells, and at least my opinion, I think Ed shares this, that is very difficult to do. And so we'll be looking also at should you be replacing wells and how many. And we'll also be touching on a little bit, as time allows, does a carbon-based injection actually displace any contaminant? The diagram that's shown here was drawn to kind of illustrate how carbon seems to move in various types of materials. In the upper part in clay, it seems to move in fractures and propagate as like almost antlers. In sand, it tends to create kind of a homogeneous pocket around the injection point until the pore space is essentially filled by the carbon, in which case it acts like a clay and will then fracture out until it finds another area where it can again begin to refill, and the process repeats itself. So in clays, you tend to get this spiderwebby, very non-uniform distribution. Things tend to move upward. If a vein finds a weak spot, such as a well, flow will then basically be directed to that path of least resistance to fill the well or the utility or whatever, the backfill. And in sands, you have this kind of a agglomeration of carbon around the injection point without very far travel. The picture that's shown here is what a water sample from a carbon-impacted well might look at, and I'll touch on that a little bit later. So as far as carbon distribution, Kentucky had done some confirmation points and continuous soil sampling between wells, or injection points, I should say, at a site. And here we show four pictures where carbon was detected essentially in each of the soils in the areas. Now, what I'll say is Ed's had really good experience with this. And in Colorado, when we have gone and done the same type of thing, we find, in our clays anyway, very little carbon, and it's very spotty and difficult to find even a few feet away. And frankly, this is something that's unpredictable, and you will find varies from site to site. This was a place here in Colorado where we had an injection point done on the left side of the screen where the yellow field book is, and we had an existing monitor well 9 10 feet away, so the distance between those 2 points is 10 feet. And MW9, after injection, was less than 5 parts per billion benzene for 5 quarters. At that point, we came in and put in a confirmation point directly between the injection point and the monitoring well to make sure that we had cleanup throughout the aquifer. And this was soil boring number 3. Soils didn't indicate very much carbon in the soil, and groundwater samples from that point measured anywhere from 35 to 116 parts per billion. And this is simply to illustrate the uneven distribution of the carbon and the variability of treatment that occur. And this site had more or less a silty clay for an aquifer. So it leads to the question of, is aquifer treatment complete? What we had done is, in the graph on the left, we had some benzene concentrations pre-injection, and you can see they were all over the board while Colorado was putting carbon in at our 200-plus sites over the past 10 years. And we tried it on a variety of places, and often, at 72% of the time, we had reductions in the concentrations in the wells, greater than 90% of the time, in the wells nearby after injection. So those are in the center post-injection or existing wells where we noticed there was significant drops of benzene in wells nearby. However, when we began to hear from vendors telling us that some of these samples from these existing wells actually had carbon in them, and we were getting calls from laboratories saying they couldn't get their surrogates back out during the analysis, we began to look at this further a few years ago. So basically, we went on for about 8 years thinking that we had been cleaning up sites, and then we heard that these samples might in fact be biased. As a result, about a year or so ago, we began to look at doing these confirmation points and getting samples nearby. So basically within 5 feet or so of an existing monitoring well that was exhibiting ND for benzene, we would install a second well, constructed, drilled, and everything identically. And we were finding that a lot of those confirmation wells, in fact, showed only a 72% reduction, and I say only, when most of 90% of the existing wells indicated we had cleanup. And in fact, some of the wells actually had, about a quarter of them had an increase in benzene. Now, I don't know what to attribute this to except to the natural variability of the aquifer and the uneven distribution of the carbon. Other than that, I'll leave that alone. And that was based on 36 well pairs that we did to compare on a variety of sites and materials. Ed, I think you picked this up from here to go through this.
I do. Okay. So this was a site that had a number of difficulties, and I think it teaches a number of lessons. The contamination had spread a good distance, and it was a shallow site, meaning that it was less than 10 foot to bedrock, and it was a saturated site, meaning that within 2 foot, or well, 2 to 4 foot from ground surface was the water table. Recall earlier when we spoke about, the tendency of the injectate to want to move upward. water is going to increase the resistance to that, so you're going to have an even harder time on a site like this with such a shallow water table of getting a good spread of your injectate. Now you can see from the monitoring well data that the concentration was significant. And it's kind of hard to see, but you can see the numbers are on the graph. And let's see, if I recall correctly, I can pick up a little pin here if I need to, can't I? Let's try a laser pointer. Aha, can everybody see that? Somebody say yes.
Yeah, we can see it.
Good, good. So here's our little laser pointer. So you'll look at monitoring well 12, for example. It's 2.7 milligrams a liter. Now, the other thing I'll let you know is Columbia Technologies did these, and I continue, while I might not like the modeling program they used, I'll continue to use it so that at least you have a consistent picture of what you're looking at. Now, the area in the angular dimensions and in pastel colors, this is the area of the carbon injection. So that would be these areas here. And some area over here. At this point, you can see what the site looked like as far as a contamination picture as drawn by Columbia. And so what we're trying to show here is the area was injected and that the plume was surrounded by wells that were not injected so that you had some control if there were push or if the plume continued to move beyond where the injection was. Okay. So let me check my date here and make sure I understand what I'm looking at. Okay, next. Now this is the picture of the benzene concentration post-injection. About a year post-injection, looking perhaps a little better, but you're kind of wondering. We're used to seeing something like monitoring well 19, which I have down at the lower part of the screen. You have hits and then you inject it, which is to the right side of the red line, and boom, you see nothing. This is, of course, what has given rise to the idea that you're just filling the well full of carbon, the idea that you can have hits and then all of a sudden they all disappear. Note that the detections in monitoring well 20 are very small, so that's kind of a perturbation of the modeling here. You're probably really looking at an area more like this. Monitoring well 28 makes the picture look a little worse than it is also. However, the modeling is consistent. So let's move and look at the next picture. Okay, now this is a mess. This is exactly what you're never supposed to do when you make slides, and that is try to teach too much in one slide. But bear with me if you will. We have the orange line and the red line. And that's where we've collected MIP and UVOS data post-injection. And I have in the picture some excerpts of that data showing you that really the only place we were finding MIP and UVOS hits, primarily MIP, was in the original area of contamination right at the corner of the tank pit. And these two arrows are incorrect. This area represented by the MIP is actually just right in here between the T and the L of the word lateral. So we come back many months later, a year after we thought, well, geez, perhaps this is just a failure of a site, and finally get the MIPs out in the field and look, and we realize, well, maybe it's not so bad, but we still have some contamination. It's kind of where you would expect it to be for the most part, and that is close to the bedrock interface, or the place where it would be precisely the most difficult to inject in a saturated soil and get a good distribution. Now, the picture that all of this is imposed on is actually monitoring well data from yet a year again later. And at that time, what you see is the only monitoring well that we're getting significant, or that we're getting interesting hits out of, I should say, is monitoring well 9, and this is approximately a 0.4. It's a 0.3 something. So we had this site. We knew it was going to be difficult and thought we failed, gave it about 3 years of time, and it really doesn't look like much of a failure anymore. We will see where it goes over the next several months. But the lessons that I think that we should probably take away from this is that some of the high characterization work should have probably been done earlier. But in coming back and looking, we realized that our monitoring wells, even those in the injection field, told us very close or very similar to the very same thing that the MIP told us. We also saw a variety of patterns from those monitoring wells. If you look on the left and see number 7, you see a gradual dying off of the concentrations in monitoring well 7 over time. The monitoring well 10 kind of did a stair step. Now, if what we were looking at were monitoring wells just simply filled with carbon, what you would really expect is what I showed you earlier on monitoring well 9. Something, injection, nothing, because your well's filled with carbon. But on the wells on this site, we didn't see that. We saw over the 3-year period of time a dying away. We also had on this site the entire area of contamination surrounded by wells that were not injected. And these wells did not show any indication of push. That is, when you put the mass into the ground, of moving the contamination away from the mass. And there are also several wells that were showed contamination that were not injected, nor was an injection done very close to the wells, and those wells also cleaned up over time. So I think there are a number of lessons off this site. Even though it's probably not one of our most impressive sites, it is impressive in the lessons I think it's teaching.
Hey, Ed, speaking of that, I had a couple of questions from the audience.
Yes, I see one of them by Rob Rule.
Yep.
Okay. Yeah, I think that question will start to answer itself, and maybe has already, but let me read it again, and I'll go ahead and address it since you brought it up. Okay, so the first part of Rob's, and I guess everyone can see this, right, that activated carbon injection seems to be transferring contaminant mass from the groundwater to the solid phase. And I would have to say at that point, yep, that's exactly what you're trying to accomplish. The next sentence, nothing is being removed. Well, it is being removed from the aqueous phase. That is true. But that's not what Rob means. Nothing is being removed or destroyed unless the carbon is eventually removed from the ground. Okay. Now, that would be true if you're willing to assume that there's no biological activity. All the vendors argue that there is biological activity. I think that's an area, and I might be stepping on Tom's toes if I go much further, but that is an area that could use a little more investigation. Now, if you look at the diagram on the site that I just showed you, I mean, clearly something is happening here. I will also say that we have, on this same site and a number of other sites, we've went back in retrospect and collected more samples, soil bores primarily, as opposed to just monitoring well samples, and sent those bores to the lab. and they've come back, looking good, a lot better than they were beforehand. So something is happening apart from the absorption of the carbon. But if carbon absorbed the contaminants in and of itself, if that's all it did, it would still be a very good remedy, and it would be consistent with at least the way Superfund looks at remedies. And so you could bind it up. The carbon is going to still slowly release over time, and you keep your overall concentrations in groundwater low. I believe, let's see, if we're at 47, the next one yours, Tom? No, I still got more. Pardon me. So we actually walked into this slide, didn't we? There's expectations associated with microbial biodegradation. It makes a lot of sense that if you put carbon, which has a tremendous amount of surface area in the ground, that carbon itself becomes essentially a new ecosystem territory that can be used to grow more microbes and spread the microbes out and decrease the concentration of the BTEX in the aqueous solution so that concentration is not toxic to those same microbes. Now, there is some question about how long the adsorption effect lasts. I would say there's no reason to believe that it's not practically infinite, because we know no matter how small you grind the carbon, it still retains its adsorptive capacity. It is also true, as I've mentioned, there is an on-off rate as there would be with any kind of van der Waals interaction. Now, it is argued by at least one of the vendors that the microbes will actually regenerate the carbon as the BTEX concentrations fall, and that makes sense. If you look at your isotherms, an isotherm always holds a balance against that chemical, say your benzene, which is bound to the carbon, versus that which is in free phase. So as that which binds to the carbon drops, the concentration in free phase drops, and they parallel each other. Why does rebound occur? Well, I haven't seen a lot of rebound, but it would make sense that if you had poor site characterization, you just simply failed to treat the mass on site, and that should reasonably result in rebound. Poor carbon distribution. And you saw that a little bit in the past slide, or perhaps you did. We're going to investigate that a little closer. Preferential desorption, that is probably more theoretical. It is true that if you, say, had a release of another chemical that was more desirable in a sense to the carbon, or bound the carbon better, had better van der Waals interactions, yes, you could drive off something. The degradation process doesn't keep up with desorption. This is, pardon me, it's not my slide. I'm not sure about that. And then finally, the degradation process is slow or stops, and that could certainly be true. When you have a variety of environments that you might be trying to inject into a number of formations, you're going to have different levels of microbial activity, or the ability to sustain that activity due to a lack of nutrients, et cetera. So, as we spoke earlier, there's still plenty of room to examine carbon as an amendment or as a remediation tool. I certainly would like to know a lot more about what's going on with the microbial community. How real is that? How sustained is it? Are we actually feeding it the right things, so to speak, the right electron receptors? There are the two major vendors that we mentioned at the beginning of the presentation take two different tacks. One of them tries to take an aerobic pathway. The other vendor tries to take an anaerobic pathway. There are pros and cons for both those pathways, and that could certainly use further investigation. And trying to understand when you use carbon in a variety of complex heterogeological conditions. So Tom and I have talked a lot. They have different conditions in Colorado. I think we both have confidence that each of us are trying to present our case as best we can from the data we have, and yet we have different results. I would say if we can recruit a third or a fourth person, we may have some yet more things to say. So Tom, I believe we move to you, don't we? Let me see, next slide. Yes.
All right, we're on the downward path here, only a few more slides. This is kind of a wrap-up. Basically, when you're doing carbon-based injection, you really need to have a good idea of what your site is. You need to have a good conceptual site model. You need to do a very detailed site assessment. You may do some high-resolution site characterization, or at a minimum, some fairly detailed soil sampling and or well installation to fully understand where your contamination is, both horizontally and vertically. You also want to do at least an estimate of contaminant mass so that you can figure out how much carbon you're trying to get into the ground. And this is where your vendor will work with your consultant and come up with at least a dosing program. And the calculation will basically be is, can we even get enough carbon in? My recommendation, again, would be to look at some of the lower concentrations. If you're focused on benzene, probably less than 700 or 800 parts per billion benzene, trying to reduce that. You'll have much more chance for success. And to reiterate what Ed said earlier, carbon-based injection is not really useful up in the Vado zone. This is more for aqueous conditions. Although carbon will absorb vapors, there are better ways to address vapor issues if that's the situation you face. Also, you should understand the basis of the design from the contractor and use an experienced design team and injection contractor. There is a bit of an art to this of knowing when to back off the pressure and let things go, and when to admit failure and pick up and move over and re-drill a replacement point, for example, if you have surfacing. Initially in Colorado, we were having injections where people would simply put carbon in the ground because that's where it would go, kind of a nonsensical answer. We also had people who would only stop when they had daylighting, and so that we didn't really know what was being treated at that point. If possible, if you want to try a test, do some pilot testing. You need to do this with the carbon material. Simply doing a pilot test with water or some other type of slurry really doesn't give you the response that you're looking for, since strictly water is going to obviously be just a fluid. It'll behave differently than this carbon slurry. And I'd also like to point out that just because you have surfacing 30 feet away or you have well impacts nearby where carbon shows up doesn't mean that that area between your injection point and where that material shows up has been fully treated. It may be very one-dimensional. Continuing on a second with our recommendations, you want to inject over very short intervals vertically, and you want to try to treat the entire vertical interval of contamination. This is where such things as MIP come in very valuably. You want to improve your monitoring protocol. As I mentioned, stop injections when you have surfacing or well impacts appear. And you want to collect some baseline data for your biogeochemical parameters such as ORP, nitrate, sulfate, dissolved oxygen, those types of things. If you have a little bit of money and can collect soil samples ahead of time and have that speciated for bacteria, or at least get a plate count type number, I think before and after will give you some ideas to whether you think or whether you have biodegradation occurring on your site or not. You need to understand your biological environment. Some sites, this isn't going to work. Not that the carbon chemistry won't work, but remember you're relying also not only on a chemical process, but a biological process to finish the job. I'd also like to mention here in number 7 that well rehabilitation doesn't work. There have been people who say that it has worked on sites they've worked on. However, the examples I've been shown are typically 1 well or 2 wells on a site, or maybe an entire site, whereas other sites don't have wells that rehabilitate. Typically, rehabilitation is done by trying to use a vacuum truck or to aggressively purge the well, either by adding water and removing it, etc. And from what I've seen is you can remove most of the carbon, but you certainly won't remove it all. And when you sample that well a quarter or two later, you'll still have carbon show up in your sample bottle. Confirmation soil borings and additional replacement wells may be necessary in your situation. And finally, remember, as I mentioned, you're creating a biological zoo down there. You're trying to induce biodegradation so you can regenerate your carbon. So periodically you may have to add more nutrients, nitrate, sulfate, etc., to boost the degradation rate and the probability that things will continue. Simply taking what the BOSS 200 or any other vendor gives you initially in the injection, you have to realize that those bacteria and those nutrients are finite, and that the bacteria will outcompete each other or may not survive in the environment you've put them in, and the nutrients will get used up over time, especially nitrate. So you may periodically need to kind of refresh the system. And finally, just to conclude here, carbon-based injection is pretty promising. I think you need to follow the recommendations I've just gone through. It will, I think, serve a lot of sites for UST sites anyway around the country. Also, you need to follow these detailed assessment practices that we've highlighted, particularly high-resolution work. Injection experience is very critical for your contractor, and more research is really needed, particularly on the biodegradation aspect of this whole process. And with that, we'll invite any questions. This slide shows both Ed and my email address if you want to email either or both of us after this. And as I understand from Drew, this slide presentation will be available for review later. Thank you all.
Thank you very much, Tom and Ed. You are correct. We will post, as I mentioned earlier, we'll post this whole presentation from today on the archives. And before we wrap things up, Ed, I think this might have been addressed on a slide, maybe 3 or 4 slides back. So forgive me if I'm double asking here, but one of the questions I have, in the injections you're referring to, just to confirm, there are no added electron acceptors to facilitate biodegradation, is that right? Is it just AC as an adsorbent?
No, there are electron acceptors, sulfate primarily.
Okay.
Oh, no, you're going to have to give it to me, Tom.
And yeah, everyone else out there, any questions for Ed, Tom, Noel? Feel free to.
Here we go. Tom gave it to me.
I think you have it.
Sorry about that. I couldn't answer because I didn't have the ball. So yes, sulfate is the electron acceptor and what we've used primarily. So yes, there are electron acceptors. You wouldn't really get anywhere if you're going the anoxic route without it. And in clay, that's really the route to go. It's where it wants to be anyway.
Okay, thanks. I'm gonna take the reins again one more time. So once again, huge thank you, Noel, Tom, Edward. I know Tom and Ed shared their contact info. There's Noel's email as well. Evaluations, like I said, you'll be prompted to a survey as you close your browser. Please complete the survey. It'll really help us out. And the webinar, as we had said, will be archived. So the entire recording, I'll post that. Within the next couple weeks, it will be up on the New Epic website. So please check that out, as well as any other information that's on there, other trainings, archive webinars, future information, things like that. And any questions, feel free to reach out to me. My contact info is right here. So anytime. And I think that's all I have, everyone. Please do the survey, and we'll talk to you next time. Thanks a lot.
Drew?
Yeah. Yes.
Oh, I wasn't sure if everybody else can hear us or it's just you and I.
It looks like there's still folks that are on right now. Yes.
Okay.